A non-homogeneous equation is one in which our differential equation L of y is set up equal to something other than 0. And what we said last week is that whenever I want to solve a non-homogeneous equation, the first thing I have to do is solve the homogeneous one. So first, solve L of y equals 0, and our solution, we're going to call it YC, the corresponding homogeneous solution, or the complementary solution, depending on which notation you want to use. If I have differential equations with constant coefficient in the L of y, second order differential equations, higher order differential equations, I can use the methods you just used in chapter 4, section 3 to solve those. As long as you can do the algebra, you can find YC. Notice I put easy in quotes here because now it means I got to solve the corresponding auxiliary equation, which is the algebraic equation, which could be of high power. And if it is, that could be a mess. But ideally, I've rigged the problem and solving this will be easy. In second orders, it's always solving a quadratic equation. Now, I need YP, the particular solution. And this becomes the hard part. Remember, our differential equation is L of y equals g of x, and the g of x part is what's not 0. So finding YP depends on g of x. The method I want to talk about today is restricted and only works when YP is constants, polynomials, exponentials, sines, or cosines. Polynomials, exponentials, sines, cosines, some combinations of these, products or sums. So what does that leave out? Leaves out all the other trig functions, tangent, secant, cosecant, cotangent. Leaves out logarithms, leaves out inverse trigs, leaves out rational functions. To an extent, it leaves out roots, but we can find a method that will allow us to work around roots. I'll save that for later. So this is a fairly restrictive case. my basic assumption is going to be that my particular solution kind of looks like g of x. But I don't know the appropriate coefficients. That's why this method is called undetermined coefficients. And then we're going to try and solve for those coefficients. But remember, the first place we start is always solving the homogeneous version of our differential equation. Once we've done that, we can work on the rest of it. So, our first example. Starts like this. Here's my second order non-homogeneous linear differential equation. The first thing I need to do is throw out the 30x plus 3 and solve the homogeneous version. So this is what you did in the homework you just gave me, chapter 4, section 3. What do I need to do? Mm-hmm.
R squared E RX.
So all I really need is to figure out the R values, right? So the auxiliary equation replaces each derivative with a power of R. This equation becomes R squared minus 10R plus 25R to the 0 equals 0. It's quadratic. Solve the quadratic. That equation. Oh, yeah. I could, but I'm going to cheat.
Or you could do the. Just add an X.
I just add an X. In this case, I get YC is e to the 5x with its constant, and then C2x e to the 5x. Because in this case, when I do that integral with the integral y1, the reduction of order thing, I always just get an X in this case. Fortunately, thank you, Lois. I have my complementary solution, my corresponding homogeneous solution. So now I have to say, well, what's YP look like? I'm going to make the assumption, since the right-hand side is a linear equation, I'm going to make the assumption that YP is also a linear equation. But I don't know what the coefficients are. This is the problem. It's a wonderful idea that my particular solution should kind of look like g of x. I can hope this is the right idea. But I don't know what a and b are. Undetermined coefficients is what I said was going on here. There's my undetermined coefficients. But I want this to work here. So let's plug it in. Which means I need y prime and y double prime for this. But this one is rigged. What's first derivative of yp? And the second derivative? Oh, that's nice. If I plug that into this equation up here, 0 minus 10a plus 25 times ax plus b should be 30x plus 3. Gather all your like terms and solve for a and b. That's it. Oh, wait a second. Right here, I get 25ax, and then everything else is a constant. So I get 25b minus 10a. And now I have two equations and two variables. The coefficient of x has to match the coefficient of x. And the constant term has to match the constant term. Yay! What do you get? And if I put that back in here, ta-da! But wait a minute. That's yp. I already got yc. Yp is now 6/5 x plus 3/5. That means I know my complete solution. That's all I needed to do. Huh. If I had initial conditions or boundary conditions, I could solve for C1 and C2. But I haven't got them, so I'm not going to. But the general idea is that if I can match yp's form to the form of g of x, it works. There's just one problem. superposition. Excuse me? What the flip? What's the superposition idea? Y'all wrote this down last week. I'm not pulling this term out of thin air. You have this written down. Back in 4.1,
Let y1, y2, yx be solutions to null y equals 0 on I. Then the function c1 cy plus c2 cy, the ck cy is also a solution to y equals 0, where c1 c2 and the ck are not.
so if I have one solution, that was equal to 0 though, right? If I have one solution and another, I can multiply constants and add. They behave like linear behaviors. The same thing is true for the non-homogeneous parts. It's the bottom of page 128 down here. And it says if I have a bunch of different pieces and I add those, well, then I have to add all the solutions and I can multiply by constants as well. So where I said here, products and sums, that means this form of YP could end up looking fairly ugly. So, promise I did not make this problem up to torture you. It's going to seem like it. Let's ignore for the moment the complementary homogeneous equation and the YC part. Just for a second. Let's only worry about the YP. Actually, you know what? No, let's go ahead and do the YC part. So first thing I have to do is solve the complementary homogeneous one. So that's 2r squared plus 3r plus 1 equals 0. What do I get for roots for that quadratic?
R plus 1, R plus 1.
Let's check. So I'm going to get 2r squared, 1r and 2r, that's 3r. What? Yeah, that works. So I get r equals minus 1 and r equals minus 1/2. So YC is C1 e to the negative 1/2 x plus C2 e to the negative x. By the way, I'm using x. If you want to use t, I don't care. But now I say to myself, what's yp? Well, yp should have its form match g of x. But g of x has multiple parts in it. I've got a quadratic polynomial. I've got an x squared. But what happens when you take derivatives of x squareds? I get something with an x. When I take the derivative of that, I get a constant, right? So as far as I can tell, the x squared part, its yp should be a quadratic equation. But I don't know what coefficients those are going to have. So as far as I can tell, the x squared should give me a quadratic, but I don't know what those numbers are. Ax squared plus bx plus c. And then I look at the trig part. And I say to myself, great, I've got a trig function. I've got a sine x. What happens when you take the derivative of sine? Which means I'm going to have both sine and cosine, because what's the derivative of cosine? So I'm going to have sines and cosines floating around, bouncing back and forth in here, which means that the particular solution should have a sine of x. It should also potentially have a cosine of x. Holy crap. Here's the fun part. I need the first and second derivative of this. And then I need to plug those back in to my differential equation, set up 5 equations in 5 variables, A, B, C, D, E. Oh, hell no. That's actually a lot easier than you think it is. Because all of the A, B, and C variables are only going to go with that x squared. And the D and E variables are only going to go with the 3 sine x. So it actually is going to be really one set of 3 equations in 3 variables and one set of 2 equations in 2 variables. It really isn't 5 equations in 5 variables. The problem is taking the freaking derivatives and plugging it all back in and gathering all the like terms. But that's algebra and Calc 1 derivatives. Look at all the hard calculus we have to do today. What's the derivative of a quadratic equation? Give me yp prime, give me yp double prime. We can do this. Derivative of ax squared. Derivative of bx. Derivative of constant c. Derivative of sine x. Derivative of e cosine x. Aha, I got to remember the sign error, sign change here. Second derivative, derivative 2ax. Derivative cosine is minus sine. Derivative sine is cosine. Those get plugged back in. 2y double prime plus 3y prime plus y. Two times this sucker. 2a minus d sine x minus e cosine x. Plus 3 times this one. 2ax plus b plus d cosine x minus e sine x plus y itself. Ax squared plus bx plus c plus d sine x plus e cosine x. And now for the nasty, ugly, horrible part of this problem. I have to do a bunch of algebra. There's only one x squared term in this whole thing, right? Right here. So on the right-hand side, I have an ax squared. What x's do I have? From here, 6a and b. Constants. Well, I've got a c here. I've got a 3b. And I've got a 4a. Sines. Sines. I have something sine x. Well, I got a d sine x here. I've got minus 3e from the second line, and I've got minus 2d from the first line. Cosines? What was g of x? When we set up the equation, equals, 2y double prime plus 3y prime plus y equals stuff. What was the stuff? Cody? X squared plus 3 sine x. So that means that a is equal to 1. 6a plus b is equal to 0. C plus 3b plus 4a is equal to 0, because that's the coefficients of all the polynomial terms. And then sine x, minus d minus, that should be a minus sign, 3e is equal to 3, and 3d minus e is equal to 0, because there's no cosines. Can you solve for B, C, D, and E? Absolutely. If A is 1, what's the value of B? That was easy. Okay, so if A is 1 and B is -6, then I get C minus 18 plus 4 equals 0. So C is 14. Now, this expression right here becomes E is equal to 3D. Plug that back in up here, and we get minus D minus 9D equals 3. What's D? This should not stump the room. What's the value of D here? -0.3. Put that back in, and I know that E is equal to -0.9. We did it. All of it. So the solution to my differential equation, y equals, give me the corresponding homogeneous part, C1 times, it's back on the previous page. And then it was C2, and then it's plus AX squared plus BX plus C plus, plus D sine X plus E cosine X. No, it's a plus. It was going to be a plus, but I realized it was plus a negative. So ignore that part. I started to write a plus sign. It's a minus sign. Phew. It worked, master. It worked. Is it long, arduous, tedious, and ugly? Yes, but it's algebra. And that is the foundational best part about what's going on here, is that I can turn derivatives and differential equations into just doing algebra if I have a good guess for my particular solution. And in this case, that's really all I need. Cody, here's where the superposition principle starts to suck big. I'm not adding. I'm multiplying. My g of x is x squared times e to the 3x, which means, what's my guess for yp?
AX squared plus C. No,
Y plus C.
plus 3C.
Again, I'm going to ask why 3C.
Oh, I just matched it up with the last equation.
Okay.
The last two Y. Y.
Okay, but here, that 2 and that 3 never showed up in YP, did they? They showed up while we were solving it, but they didn't actually show up in the solution itself. So what I did is I said, oh, when I want to find the YP, I look at each of the two pieces. This is going to give me a quadratic. And this is going to give me trig stuff. And I added them together because this was being added together. So now I'm going to say the same thing. I've got a quadratic. So I should get a quadratic. I should get ax squared plus bx plus c. And from the e to the 3x, the derivative of e to the 3x is number e to the 3x, right? But that's a coefficient. So really, when I start doing the derivative of e to the 3x, I get more e to the 3x's. And so I should get an e to the 3x part. But since these parts are multiplied, so are these. And that means when I go to do my first and second derivative, I've got a product rule. And gathering my like terms is going to be uglier because my derivatives are going to be uglier. Is there a nice, easy way to do this that would avoid all of this garbage? No. Because trust me, if there was, that would be where I would start. What about the homogeneous part? I didn't talk about that at all. What about the homogeneous part? What's the solution to the homogeneous part? I rigged this one again. What's the quadratic equation I need to solve?
R squared. I just make it R plus square root of B. That's C squared.
Unfortunately, no, because it's the sum, right? So this is actually giving me r squared equals -3, which gives me r equals a complex root. Fiddlesticks. That's okay. I'll live with that. Because what happens when I do complex numbers? Oh, I wish. We use Euler's formula. And we get our complex form with the cosines and the sines. So, wait a minute. I screwed up. I screwed up, though, before I get there. What's the square root of -3? It's square root of 3i. Cody, I screwed up. Catch me at it. Okay, so yeah, I'm going to get cosine square root 3x plus sine square root 3x, C1 and C2 respectively. C1 on the first one, C2 on the second one. If I had a real number here, something plus or minus square root of 3, then it would be e to that cosine and e to that sine. But since there's a 0 here, what's e to the 0? So I'm multiplying this cosine and this sine by 1. Makes my life easier. So now I have to take the first and second derivatives of this, plug it back in. No, forget it. We'll do it later. It works. It's just ugly. But I promise there's a reason I wanted to see the corresponding homogeneous solution. I kept saying we should do the homogeneous first. And then when I did this example here, I didn't do the homogeneous first. That's a problem. I got away with it in this example up here because the cosine and the sine have nothing to do with this quadratic or this e to the 3x. But let's look at this sucker. First thing I need to do is solve the corresponding homogeneous version. So give me a quadratic equation and give me the roots thereof. And then let's get YC. Even if I don't like it, I should be able to do the quadratic formula in a split second or 3. What do you get? Hey, wait a minute. That's a repeated root, right? So what's YC? Here's the problem. This is absolutely 100% correct. Now I start to look at YP. I see an e to the 1/2 x again. I can't use another e to the 1/2 x. It's already there. It wouldn't be independent. As a matter of fact, it's already there twice. I need to have a linearly independent solution. I should go through that integral again. I think I'd rather hit myself over the head with a brick. But when we went through the integral and we did e to the 1/2 x, we got x e to the 1/2 x. So maybe I use that. Wait, no, x e to the 1/2 x is still here. So I need to do the integral again. You know what I'm going to get then? That's it. I keep adding x's until I get a power that does not appear in the corresponding homogeneous solution. In general, this is what's going to work every time. So now I will say that what I should get for yp is, wait, I have 3 plus e to the x over 2, right? So I should get a constant and then b x squared e to the 1/2 x. And now I can go through what we just did. I can take the first and second derivative, which is going to give me a couple of product rules and some distribution I'm not going to be happy with. I will learn to lump it. And I can make the following general statement. If yp should contain terms that appear in yc, multiply by the smallest power of x needed to remove the duplications. That is a sufficient behavior to guarantee me a linearly independent piece in yp. We had an e to the x over 2. We had an x e to the x over 2. I need the next power of x up. That's all it needs. But this is always why we should do the corresponding homogeneous part first, to make sure that we're not seeing a duplicated term. So here, in this example, the first thing I do is I look to solve y double prime plus 4y equals 0. The quadratic that goes with that is r squared plus 4 equals 0, which means I get complex solutions. R squared equals -4, r equals plus or minus 2i. My corresponding homogeneous solution should be C1 cosine 2x plus C2 sine 2x. And there's the alarm bell in my head. Ming, 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 ming. We effed up. No, we didn't F up. I have to look at my particular solution, and it should look like something with a sine 2x in it. I already have that. So I multiply by an x, and I get an x sine x. Sorry, x sine 2x. What else do I get? There's another piece here. What's the other piece? But what's the something? I already had the sign. Sign's up here. Whenever I start taking derivatives of stuff with signs, I'm gonna get cosine. But cosine already appears. Nope, because I'm gonna get an x. There we go. By the way, eventually we will show that A is 0 and I only need the B cosine 2x part, but I got to get there. And that's going to take some work. I am not done with this section. There's more to be done here. This shows up a lot. By the way, this behavior, what does x cosine x look like? Cosine wiggles back and forth. If I multiply it by an x, it wiggles back and forth and gets bigger, doesn't it? Remember our bridge, galloping Gertie, and how it reinforced the vibration? Because the vibration had the same period as the solution. The 2x in the g of x there is the same 2x that shows up in my homogeneous solution, means I get that reinforcement. More on this when we talk about the actual vibrations. I'm not done with this section. I have more to talk about on Friday. I will see you all then.